Hello, everyone. Welcome to the Nomads podcast. I'm your co host Prachi.
And I'm your co-host Bhavya.
The universe is about 14 billion years old. Have you ever wondered, how do we even know the age of the universe? How can we look up at the sky and read time itself? We do this by studying the afterglow of the Big Bang, called the cosmic microwave background radiation, or CMBR. It's relic radiation from the very beginning of the universe. Physicists build ultra-cold microwave telescopes, cryogenic cameras with incredibly sensitive detectors that can spot tiny temperature changes and faint polarization, and even see how gravity bends that light. Our guest today, Dr. Vavagiakis, is an experimental cosmologist at Duke University who helps design, build, and calibrate these instruments for various experiments like ACT, the Simons Observatory, CCAT-prime, and CMBS4. Her expertise spans cryogenic instrumentation, superconducting detectors, and extracting meaningful physics from enormous observations. She also writes children's science books that turn big cosmic ideas into playful stories for young readers, bringing neutrinos, black holes, and photons to life. She believes kids should have access to, even if not a complete understanding of, the latest discoveries and complex ideas. If you're someone who wonders how we know the universe's age, or someone who likes telescopes, you're in for a delight. So, let's go! Professor Vavagiakis, welcome to the Nomads podcast.
Thank you so much for having me.
So, cosmology has been on the forefront of physics forever. And one of the biggest breakthroughs has been the discovery of cosmic microwave background. And what's fascinating is that it was discovered almost by an accident in 1965. And now, decades later, we're still not being able to completely understand what's going on. So how about you start by explaining what actually is cosmic microwave background and what is it about it that is so hard to comprehend?
Yeah, definitely. So when you look out at the night sky, you look at these stars, maybe some galaxies, and you're not seeing that light as it is today. I think that's one of the first things we learn as children, looking up and in wonderment at the Milky Way and thinking, wow, this light has taken so long for it to finally reach Earth. And the natural question then you might ask after that is, well, can I look a little further? And the answer is yes, you can look out further and see farther back into time because light has this finite speed of travel and you only see it finally after it traverses these extremely long distances. And so you start to ask, how far back can you look in time? And the answer to that is this cosmic microwave background. It's the oldest light that we can possibly observe. It was emitted only 380,000 years after the Big Bang. So we are not quite looking back to the start of it all. We want to. We can't for reasons I can get into. But this is the oldest possible light observable. And these photons have been traveling for some 13.8 roughly billion years before we capture them with our telescopes here on Earth. So the reason we can't look back farther is because the universe was too hot and dense at that time. So the photons or light particles were just constantly bouncing around in this very hot and dense plasma, unable to travel freely until the universe expanded enough and thinned out enough that we can observe that light. So not only is this light the most ancient, and we can learn about this baby picture of the universe, but also those photons have traversed massive gravitational wells. They scatter off of material in these more familiar objects like galaxy groups and clusters. And so we see a wealth of signatures in this radiation, and we've been working on, for the past several decades, piecing it apart, learning about the origins, evolution, composition of our universe, and also gleaning insights into astrophysics and the distribution of matter at these very large scales. And the reasons that it's so difficult to measure some of these signals is they're very faint. It's very challenging to have high signal to noise or high significance measurements for some of these observables that we're interested in studying. And so today we are working towards making better measurements of this light. We've already really done a remarkable job. I say we, and I don't mean me necessarily, because I'm a newcomer to this field. I was not active in the 90s, but people were making great leaps to understand the standard model of cosmology, lambda CDM cosmology. And it's actually remarkable how much we know, but a lot of what we know now is known unknowns. So we have this whole dark sector of the universe. We only understand about 5% of what the universe is made of. 95% of the universe is in this dark sector, dark matter and dark energy that we don't know the properties of whatsoever. And so, I mean, other than dark matter clumps like gravitationally, and dark energy is accelerating the expansion of our universe. But other than that, there are many things to understand. And so while it's been remarkable how much we do know today, we are building these new telescopes, new cameras, working on technologies to make better measurements, and are excited for the next generation of measurements to come, which is right now it's a great time to record a podcast episode on cosmology because there's so much happening.
That's great. So we can actually get a little deep into this. The cosmic microwave background is basically uniform and isotropic, but the detectors have also captured many fluctuations, tiny fluctuations. So what exactly does the radiation, what information does it carry, and what do these anisotropies correspond to? What do they mean? Is there a pattern behind them? So if you can talk about that.
Yes, so there's, again, a wealth of signals that are present in these anisotropies. And I think probably you're thinking more about primary anisotropies. There's two types, primary and secondary. Secondary anisotropies are the things that are encoded after the CMB photons were released. They travel and interact, but we can put that aside for now and just talk about the primary anisotropies. And you're indicating this very important principle that actually ties back into one of our biggest unknowns, which is this high degree of isotropy across the sky. You look at one portion of the sky, it looks the same as the other as long as your resolution isn't too high in resolution in terms of contrast, not in spatial resolution. But you look at one part and the other part, it's all this black body spectrum, 2.7 Kelvin radiation. And the question is, why should that part of the sky and this part of the sky be at the exact same temperature where when you wind the clock backwards, those areas should not have been talking to each other. They shouldn't have been in causal contact. And so one signature that we are now on the great hunt for, this is kind of like the holy grail in the world of CMB physics, is trying to find this signature of inflation. So a postulated period of rapid expansion of the universe at early times could explain why we have these two disjoint, or any place you're looking outside of a certain radius, parts of the sky having been in causal contact with one another. And the signature of this period of inflation shows up in primordial gravitational waves. So you might be familiar with gravitational waves, like from LIGO. We've seen this amazing news come out about these collisions of massive objects later in time. We're not talking about that. We're talking about the quantum nature of the very early universe, where small fluctuations at, again, the very earliest times encoded certain signatures in the cosmic microwave background, in this case in the form of polarization. Not too dissimilar to the way light is polarized when you're looking at it with or without sunglasses, but more so in the pattern of the light in the sky. And those signatures were encoded because of this early fluctuations, and indeed those same fluctuations also seeded the structure that we see today, because it's another unknown problem is, if the universe is so isotropic at these scales, why is it clumpy as well? And the clumpiness can be answered by these early fluctuations that were the earliest seeds of differences across space that matter could then clump and form large-scale structure.
So if I understand this correctly, these quantum fluctuations were amplified because of rapid inflation, and is that
so the universe is expanding and stretching these spatial scales until they are macroscopic.
I see.
So this is interesting because there's also a lot of debate about what kind of inflation is the one that we need to study, right? We have different inflationary models right now, and we don't know which one's correct. So do you think this can shed a better light on what is the correct way to understand this?
Yeah, so this is one of the only tools that we'll have available to us to rule out models and rule in others. So like you mentioned, there's a wide diversity of models that can explain this. And to give a little bit more context to the way this all works is theorists are very talented at coming up with explanations for our observables. Experimentalists come in and make measurements and say whether or not the observed universe is in agreement with the models. And so it's this conversation that we're having over time. And theorists have come up with so many incredible theories that experimentalists have now been able to rule out some. We've constrained the parameter space quite a bit. But now we're at this juncture where we thought we might be able to measure this signature, which is encapsulated in the tensor to scalar ratio. That gives an indication that these tensor modes are what causes the polarization signature of inflation in the early universe. And we've been trying to measure this for quite some time and aren't making a definitive high signal to noise measurement. We are only able to rule out various numbers because we're improving the constraints. And when you're looking towards the near future with these new experiments like the Simons Observatory, we'll be able to improve those constraints significantly, which is exciting because that's the only way we're going to be able to potentially make a measurement, but that doesn't guarantee that we'll make a definitive measurement of this important quantity. But that doesn't mean it won't tell us nothing. We'll still be able to count out some models that are now going to be in some level of disagreement with the information. But if we find that measurement, that's really the pinnacle achievement that we're trying to make.
Right. So there's like a bunch of tangents that we can go on by what you just described. One thing that I will go ahead and ask anyway. So this signal that can perhaps be a smoking gun, will it also, which is the signal for inflation, which will it also shed light on the matter-antimatter asymmetry problem?
Yes, so there are a number of tools we can use to get at this big problem that you're referencing, which is saying, why are we here living as matter right now, where matter and antimatter should have been created in the very early universe in complete equity, and yet there's a small asymmetry that is unexplained in our current understanding. And so one way we can look at this is by learning about particle physics. So we can use the universe to study quantum effects like inflation, like I was just mentioning, and also particle physics at large. So we look at how particles were created in the early universe. Cosmic microwave background measurements give you constraints that tell you about how the standard model of physics came to be in the course of the timeline of the universe, and also glean some insight into maybe there are some particles that we did not expect, such as species of neutrinos that we weren't aware of, or the like. And if we could use the universe to understand particle physics in this way, it can potentially address the matter-antimatter asymmetry problem by giving us a more complete picture of the fundamental physics of our universe.
Right, because I'm particularly interested in this because very recently, with a bunch of collaborators, we put out a result that understands how well, I mean, still using toy models, 5 to the 4 theory and so on, that how these small asymmetries can lead to can amplify and lead to a more matter than antimatter. But not studied full blown, like with all matter fields and so on, but like with one scalar field and see if there's like 2 different types of excitations and if one dominates and the other one gets suppressed by something like that. So a signal like that can be very it can help these ideas and to understand what the problem is.
Yeah. One of the most remarkable things about the cosmic microwave background is it's giving you this insight into this extremely high energy regime, which we're not able to probe here on Earth because it exceeds dramatically the energy levels we can reach in our accelerators and things like at CERN, for example. And when you access those energy scales, you're able to probe physics that we might be less familiar with today, like when you're talking about scalar fields or things like that in inflationary models. I don't think people have a great grasp of, non-physicists at least don't have a great grasp of what that means, but these were really the bread and butter of that time that then funnels the energy into the more familiar particles as the universe evolves. And by studying this extremely high energy regime, we can get at the types of physics that you're describing, and it's exciting that we can measure something like that.
Exactly. All right, coming back to CMBR, maybe let's take like a historical route and some of the early experiments, for example, Planck, COBE, WMAP, were space-based, and we see more experiments coming up which are ground-based. So can you tell us how these experiments differ and what exactly are they looking for? Well, I would think very naively that something in space would be better, but the Akatama telescope that you're a part of as well, and the CMB stage 4 is also on the horizon coming up. If you can,
it's been canceled.
Oh, really?
Yeah.
Oh.
Sorry to say this live, but unfortunately, recent news in the field, which has been really disappointing, is the NSF and the DOE recently canceled CMB stage 4. So while the collaboration remains alive and we're trying to figure out our next steps, we no longer have the support for that particular experimental configuration. And I can get into a little bit of why that is. And
Please.
Part of the issue is the lack of access to the South Pole site, which was critical to CMB stage 4, at least in the configuration we had originally proposed. And in addition, the Simons Observatory is doing a really great job at fielding small aperture telescopes, which then have decreased the contrast and the improvement in the expected sensitivity to R that CMB stage 4 would have offered. It's more complex than what I have just said, but those are some key elements that go into this large discussion in trying to work with the funding agencies to support such a large experiment. So unfortunately, we will have a future in CMB physics, and we will have a next generation just by a matter of necessity, but it may or may not be this configuration of that was called CMB stage 4.
Because while preparing for this, I was actually going through, and so they perhaps have not updated their website, and it still says that things are up and running.
I think CMB stage 4 has one line on the website right now that somebody put in that said, like, it is canceled.
Really?
But the whole website has not been updated. Yeah. So.
Anyway, coming back to the differences between ground-based observatories and space-based.
Yes. So I, too, would be excited to see more things in space. The problem is it's very expensive to launch things into space. Okay. And when we were looking at fielding, we've already talked about inflationary science, but we've not talked about the complete picture of CMB science. Many interesting observables can only be seen when you look at small angular scales. So you need high resolution images. And the only way to achieve high resolution images is to have a larger telescope mirror. This is just a simple scaling. With the larger the mirror, the smaller the scales you can see, and vice versa. So inflationary modes benefit from larger angular scale measurements. So we have these smaller aperture telescopes. That's what I referred to for Simons. But these large aperture telescopes at 6 meter mirror scale, or SPT, the South Pole telescope, has an 8 meter mirror. Those give us unparalleled resolution to look at things like secondary anisotropies and to what we call de-lens the images that we're going to be using for inflationary measurements by doing careful basically cross correlations. You're looking at the same sky in different scales, looking at different foregrounds, lensing effects from gravitational clumps in front of the CMB. And only by combining all these things are you going to make the best measurements that you can. So we don't have the money and the means to field many large aperture telescopes into space. So the advantage of a space mission is that you see the full sky. You obviously don't have the ground to contend with. On the ground you do. You also don't have Earth's atmosphere, which absorbs exactly in the wavelengths that we're interested in studying, which is pesky, and why we go to high elevation sites like the Atacama Desert, which has low precipitable water vapor, just less atmosphere to look through. So we're kind of trying to go to space on land by choosing these extreme sites. That's why also the the South Pole is such an interesting site. It's because it too has a very stable atmosphere, especially for these tensor to scalar ratio measurements, which do deep foreground sensitive images of the CMB. That's another exceptional site to go to that has a low element of atmospheric contamination. If you're in space, you don't need to deal with it at all. Right. In space, though, you launch this thing, you can't go out and fix it if something breaks. If you want to upgrade it, Sorry, it's in space. So as somebody who builds the instruments, I'm very grateful that they're on Earth so that I can go fix them, upgrade them, make changes. And one of the great things about building these platforms on Earth is that we're able to drive a truck up there and change out the technologies over time. So you referred to the Atacama Cosmology Telescope.
Right.
That had seen a variety of different, we call them receivers. These are the cameras we put in the telescope. And I think just a differentiation for people who aren't used to thinking about this, the telescope is basically the large optical mirrors that shine the light into some kind of instrument space, and then we build these cameras and field them inside of the telescopes. Sometimes for small aperture telescopes, it's a bit more integrated, but you can think of it roughly as telescope is the optical configuration that brings your light from the sky into the space, and then the camera is what has the pixels, just like you would expect from a camera in your phone. And so we can field different generations of cameras in the same telescope when they're here on Earth. But it really, cost is another big reality that we have to work with.
Yeah.
Gotcha.
So talking about your role, so you've been part of many, like one of the biggest collaboration experiments. How could you talk about what your role has been exactly in all of this?
So that's taken a bit of a winding path as I started in the field in graduate school and kind of moved along in my education and expertise. But I'm a part of the camera side where we build the detector arrays. So I contributed to measuring these. The scheme of this is usually these arrays of detectors are fabricated at institutions like government labs that have a specialty in fabrication for the types of detectors that we use. So we work with them to make the detectors, we bring them to the institutions and test them in our cryogenic test beds. So I have a long history of expertise with the cryogenics that make up the camera systems. So we can get into this. This is all the pixels are superconducting, meaning they need to be cooled cryogenically in these systems. And we just have one now in the basement here at Duke for the very first time, first dilution refrigerator from Blue Force here, which is exciting. And so we put these inside of our cameras to cool the pixels. So I've been on the pixel side of things. I then designed the mechanical structures that make up the actual supports of the cameras themselves. So the vacuum shells, the cold stages in between, and all of the cryomechanical supports that then allow for fielding these detectors, which need to go into basically this big onion of cryogenics. And if you want to get into cryogenics, I'd be very happy to talk more in details about that.
Like, talk about what are cryogenic detectors.
Yes, okay. So we are trying to measure these really small and faint signals. The best detector we can build to do that relies on a quantum principle. This is the first generation of quantum technologies, not the second, so it's not like quantum computing, but it's still a quantum sensor relying on superconductivity. And a superconductor is a metal or material that has a very interesting property where it loses all of its resistance past a certain temperature. So suddenly there is no resistance anymore. And you can use this property by, if I could draw the graph, there's like a steep transition to that point. If you operate that detector on that transition, it turns into a really sensitive thermometer in terms of this transition edge sensor bolometer. Now it's in the name, right? Transition edge sensor. Bolometer indicates temperature sensitivity. And so a very small change in temperature will create a large change in resistance because you're operating it on this like steep transition. So we leverage that principle by fielding these, and they're so small, you'd have to look under a microscope to see it. But when you look just with your eyes at these wafers, they're about 15 centimeters in diameter, hexagonal, shiny things, and they have many cross-shaped antenna all over them. Each one of those antenna feeds a number of detectors, and the reason they're cross-shaped and at different angles is that they're polarization sensitive. So all of this to say, we need to cool down those detectors past this transition temperature so that we can operate them at that transition. And that transition temperature occurs at around 100 millikelvin, so near absolute zero. You can only achieve that by designing this cryogenic system, which has some kind of a technology in it, like a dilution refrigerator, which is a very special kind of refrigerator that cools down to this extreme low temperature. You need to do this in a vacuum state because otherwise you'd be freezing gunk onto everything. And so we have to build these giant cameras. They're giant because we need to field more and more of these detectors to improve our sensitivities. The detectors themselves are already pretty much as good as we can make them. They're background limited, meaning they can't be improved in terms of a detector technology on their own anymore. We're still making improvements, though, in terms of readout, simplicity. I didn't get into kinetic inductance detectors, which we're developing for CCAT right now, which are a different type of detector technology. Same deal, though. You need to cool them down. They just have a simpler readout scheme. Because readout is a key challenge here, since you can't bring in a pair of wires to every detector or pixel. You would overheat your system. It's just too much thermal load. You can only do this by having multiplexed readout, meaning you read out multiple detectors on one set of lines of wires. So there are a variety of readout schemes. We're still making great improvements in that area, and we are improving the detector and readout technologies overall, but the only way to get improved sensitivity of the CMB is to field more detectors. So by scaling up, that's why we're building these huge instrument spaces, these new telescopes, and Simons Observatory fielded the largest millimeter wave camera ever built. And so it's a really impressive engineering achievement, and it's all at the heart of it requiring cryogenic systems. So these dilution refrigerators I keep referring to are the same type of technology used in quantum computing. I don't know if you've seen that kind of layer cake of shiny golden plates. We have that too. We just have different systems of wires inside.
I see.
Right.
Yeah, I feel like I just went on a long conversation there. So direct me wherever you're
that's
interested.
fine. So I was going to ask that in these huge collaborations, like a lot of areas of science come together. You mentioned quantum sensing and so on. And are you actively working with all these people?
Yes. So the side of my work that I didn't reference is the analysis side, where I actually study the light that we have taken images of, and then study the secondary anisotropies specifically. I'm interested in the Tsarnaev-Zldovich effect, which is how galaxy groups and clusters distort the light. So these massive collaborations are kind of a wonder of human ingenuity, because we're bringing together hundreds of researchers from across the globe, and it's been wonderful to work with everybody. So the way this tends to work is you have smaller working groups, people who are focused on the detectors, people who are focused on the cryogenic receiver, people who are focused on the secondary anisotropies, people on the primary, and all the different science cases might have some different subgroups, and there are many people involved in many of them, but I would think of it kind of as one of these branching network diagrams where people might be in a number of working groups, but certainly not in all. And there's also all the leadership, the project management, the operations, etc. And so I'm a part of many of those, but certainly not all of them, or else I would never be able to work, because my schedule would be all telecons.
And I mean, that explains why such projects go to national labs, because I've experienced, I was in Los Alamos last summer, and I've experienced how, just people from different backgrounds just come together and they work on, like you said, almost like a branch where people are just working on many different parts, and then there's so many connections and so on.
Yeah, definitely.
So which national lab was this?
So we work for, or not with, resetting. So we work primarily with NIST for a number of our detector arrays. That's the National Institute of Standards and Technology.
Right.
They have a number of locations. We work with the Boulder location right now for developing these kinetic inductance detectors, but also many other labs specialize in detectors for cosmology. So Fermilab, Argonne, and Berkeley Lab are all in the field of creating and fabricating these detector systems.
Right. So you were talking about galaxy clusters. Let's talk about what these are. So I would understand, much like how black holes act as laboratories for quantum gravity, these can be called as cosmic laboratories. So starting from what are galaxy clusters, how do we actually use them to probe the matter in universe?
Yeah, so galaxy clusters are the largest gravitationally bound structures that we have in the universe. They are giant clumps of both baryonic or normal matter and also dark matter. And inside of these systems, we have galaxies like the one that we live in here, our own Milky Way. And these are essentially the bones of the large-scale structure of our universe, and we can take X-rays, quote-unquote, of those bones by shining the CMB through them. And by studying the Sinayev-Zldovich effect, which is present, by the way, in all baryonic matter, it's not just galaxy clusters, it's just that these are so massive they provide high significance measurements of the SE effect. But we're actually able to map the SE effect across the whole sky and make some really beautiful measurements of where this matter lives in our whole universe. But if you study clusters and groups are just a name of smaller mass. Cluster-like objects are still groups of, well, clumps of, not to use the same word to define it, clumps of galaxies. And if you study these with the backlight of the CMB, you can see not only their thermal properties, so the energy that's in the hot gas pressure in these clumps, but also the way they're moving around in large-scale structure. And by studying the gravitational infall of these groups and clusters, you learn about general relativity, maybe models of modified gravity. You can start testing the way that we have modeled gravity on large scales. You can learn about dark energy because we are expanding this universe. You know, that impacts large-scale structure. You can probe neutrino physics and potentially start to weigh in on this baryon or matter-antimatter asymmetry and learn about particle physics at large scale. So basically any input that has gone into creating large-scale structure. For example, neutrinos free stream relativistically at early times. They don't clump down the way that normal matter does. And you can use that principle. There are some beautiful simulations where you can kind of toggle the mass that's in neutrinos in our universe. You can see large-scale structure either smear out or become higher contrast depending on how much mass is in neutrinos. So anything that has gone into creating large-scale structure, we can then study by leveraging these massive structures and how they exist in large-scale structure.
Got it. You also mentioned, like before we move forward, what is SC effect?
Yeah, so this is the Sinayev-Zldovich effect, and it is how CMB photons change when they scatter off of electrons across the whole universe, but we see that signal especially strongly in galaxy groups and clusters.
Right, okay.
So again, looking at these galaxy clusters, you also talked about this before. We receive, multi-wavelength signals. So what maybe talk about what different wavelengths correspond to, how do different wavelengths correspond to different models of cosmology, and do they correspond to different physics and so on?
Yeah, so multi-frequency probes are one of the key next steps that we're going to have to untangle some of the key information we need to proceed with better measurements of these observables, how we're going to constrain things like foreground emission that would contaminate measurements that would otherwise give us more insights into the tensor to scalar ratio, and so much more. We need a wide frequency coverage in order to make our next steps in the field. And there are a number of frequencies that we've been observing in already, and we're about to open higher windows with the CCAT Observatory, which I'm very excited about. For measuring the cosmic microwave background, you can plot out a black body spectrum of the CMB and just see from the peak of that kind of bell-shaped curve where you might want to be observing. And then you have to dance around the lines that you need to avoid because they're absorbed by the atmosphere. So you have windows that you can observe in, and that's where we target. So the CMB peaks around 150 gigahertz. It's in the word cosmic microwave background. These are microwaves. It's the same length scale as is in your microwave at home, so millimeter wavelengths. And we do both low and high frequency measurements within that, so say around 30 gigahertz up to around 220 gigahertz. And this gives you key information. For example, the Sinayev-Zldovich effect has a null, meaning you don't see any signal in terms of the thermal SC effect at 220 gigahertz. So if you look at the sky, that might give you some insight into things like emissive radiation that would otherwise contaminate your measurements, because you can't be seeing this effect in that frequency band. You can go back to your other frequency bands and use that information for your benefit for making higher significance measurements by reducing the systematics present in the effect. So very important for systematics, important for untangling these spectroscopic types of effects that matter in terms of what frequency you're looking at. And then pushing above that is going to be very exciting, because for the first time with CCAT, we're going to have full sky coverage of the same survey areas that the Simons Observatory will be observing, but at sub-millimeter wavelengths, which means we're going to higher frequencies.
Right.
So we're pushing up to 850 gigahertz with CCAT. And that's, again, smaller than a millimeter wavelength. And what that means is we're going to have better coverage to constrain these foregrounds. We're going to improve then things like the bias on the measurement of the tensor to scalar ratio, and get new insights into the Tsarnaev-Zildovich effects because of the spectral coverage that we're going to be getting. And then within these frequency bands, I said the word spectroscopic earlier, I meant spectral. Spectroscopically, though, you can use things like Fabry-Perot interferometers or on-chip spectrometers, new detector technologies, that will give you the ability to kind of slice through time in redshift space during key epochs of the universe's evolution, like the epoch of reionization. There we go. And the epoch of reionization is a critical period in the evolution of our universe, where the first light sources flicker on and reionize the universe. And this is a very unknown part of the universe's history, which we can start to study in these same wavelengths. So for CCAT, we're deploying some of these at these higher frequencies, and it's going to be an exciting time for cosmology. This is not, it's after the CMB was emitted, but it's still new windows into the evolution of our universe.
What is this tensor ratio? What does it tell us?
So that tells you about the quantum fluctuations that were seeded by inflation.
Okay.
Right. So because your expertise is in detector design and then analysis later, maybe for someone who does not know a lot about telescopes, can you give like an anatomy of a telescope? What are some of the key moving parts that come together? I know you briefly mentioned about what exactly happens, but some of the key moving parts and how does the entire thing come together?
Yeah. So you need to get light from the sky onto your detectors. That's the whole name of the game.
Right.
Sounds simple. It shouldn't be this hard. And yet there are a lot of pieces that go into it. So the first step is the telescope. Inside of the telescope, there are mirrors. Those mirrors focus the light into the receiver space that you then put your camera. Those mirrors look different than you might be familiar with optically. All of our intuition as humans come from our eyes, right? Those are our favorite optical instruments. And for millimeter wavelengths, since we do not see in millimeter wavelengths, it's a little bit less intuitive. So the mirrors that we use tend to be these aluminum panel mirrors. So it really doesn't look that shiny, to be honest.
Right.
But it's shiny just fine for millimeter wavelengths. So you have these metal, flat pieces that then shine the millimeter and sub-millimeter wavelength light into the instrument space. So what you're looking at in that case, and I'm talking about the large aperture telescopes right now because that's my area of expertise, it's a multi-story building, basically. You can walk all up and down it, both inside and outside, and these mirrors are 6 meters in diameter, then the structure needs to be larger than that to accommodate them. And then inside of the instrument space is where you put your camera. And so being involved in the development and design of these cameras, there are a number of elements that you need to consider when you're building them. The outermost shell is vacuum shell. That's so that you can pull vacuum in the system to have your cryogenic systems be able to successfully cool your detectors. What that means is the light on its journey has now bounced to the mirrors or onto the mirrors and into your instrument space. It has to pass through a window, but that window needs to be vacuum tight. Okay. And so what we use is usually there are a number of options, but one of the things that we're using the most for SO and for CCAT is ultra high molecular weight polyethylene. It's just a plastic and you can't see through it with your eyes. So that's another not intuitive thing. It's just a piece of white plastic, but again, fine for the frequencies we're observing. And so what that does is it's transmissive without being non-vacuum tight. You get through that and then you're not ready yet to hit your detectors because you are not, it's all of the wavelengths of light, right? It's still just the sky. We then select for different wavelengths, which reduces the load, the radiated or the the radiative load of the light onto the detector arrays, but defines as well which frequencies are actually getting to our pixels. And so you have a series of filters. After those filters, you're just kind of diffuse light. You need to be focused onto the arrays. So you have then a series of lenses as well. We use silicon. There are a number of interesting engineering challenges there as well, where you can etch these surfaces to have anti-reflection properties. So there's a bunch of optical understanding that needs to go into designing all of these elements. And then at the very end, you have filtered light that's been focused and maintained in the sense that it's not reflecting off of everything and just bouncing around and being lost. And then that finally gets to your detector arrays, and it's focused onto the detector arrays through feed horns, which couple to the light before finally depositing it onto the antennas. And then you record that signal by measuring the small changes over time. Like I mentioned, this is a time stream data, meaning you're just constantly measuring it. It's not taking a picture like you would think of with your iPhone. That data is read out through a complex readout system and then recorded, and then that data needs to be shipped to wherever it needs to go, recorded in drives and sent to computers. And then finally, the map makers create maps from the time stream. And while this time stream is being recorded, the telescope itself is constantly scanning, so it moves across the sky over time. And that helps for things like reducing atmospheric noise, because you're constantly scanning around, the atmosphere is changing over time, you're basically averaging down on the signal of interest.
That's interesting.
So I have two questions here. First, what is a typical timeline starting from the designing of the telescope to getting something tangible, like some data?
Yeah, great question. I don't know a timeline without the pandemic, so I will just say that. But the way this worked, for example, for the Simons Observatory, we found out about the creation of the Simons Observatory through generous gifts from the Simons Foundation. Jim Simons is the name behind the Simons Foundation. And I want to check this before this is published, that is what initiated the origin of the Simons Observatory. But I'm pretty sure that the news came out that we're going to basically combine forces with the Atacama Cosmology Telescope and the Simons Array, people who are individuals also working on telescopes in the Atacama. And that was in 2016.
Okay.
So I was in grad school at the time, and it was very exciting. And then we got to work planning this instrument. And so I had some meetings that I still recall as some of the most exciting, where we, at the chalkboard, talked through what the Large Aperture Telescope receiver might possibly be like, and just, back of a napkin type of conversations about what this thing could look like. And now that's that largest ever millimeter wave camera, and it just existed on a chalkboard one summer. And so many, many years of work went into that. I guess almost 10 years now. The pandemic did set that, made that a larger number than it would have been otherwise. At some point, you move from design to development, where laboratories are building these, national labs are fabricating the detectors. Institutions like UPenn, which had the high bay that eventually developed the Large Aperture Telescope receiver, or San Diego, for example, is one of the institutions that developed a small aperture telescope. These key institutions develop the systems with teams of students. I mean, so many wonderful students and postdocs work so hard to build these things over very many years. And then eventually they're ready, they're tested, they're validated in the lab, and they're ready to ship. And then we have to ship them to Chile, which is a very long journey. We go by the ocean, we put them on boats. Unload them, bring them up to the mountain, and then work on putting them together. And so I got to go out for a week and help put together one of these small aperture telescopes, and it was an incredible experience. A lot of us spend way more time than just 1 week out there, and so it's very impressive the type of physical labor that goes into putting these things together. And finally, when they're together, we can start taking data. And Simons Observatory just turned on for the first time this year. So we have first light, we're observing, we're moving into operations. That means we're focused now not so much on designing new things, but instead just taking the data, managing what we're doing day to day, and starting the data analysis, which is extremely exciting. Maps are already being made. So that's kind of the lifetime of one of these. For CCAT, I'm very excited because we're at the earlier stage of that, where the telescope is just being built. We are nearing the end of our laboratory preparation phase for some of these cameras, and we're going to get to go and put them up there, and I'm thrilled to be able to do that next year.
Oh, wow. Okay. And the second question was, you were mentioning that once you get some data out of it, then you build these CMB maps. So how often do these maps get updated?
That's a great question, and something that varies a lot. Usually there are seasons of data that are incorporated at a time. Mm-hmm. So it's not like you're constantly updating the maps, because that would be a living nightmare of work. Usually we have data releases, and those happen every couple of years. It's hard to say exactly how many. I would say 2 years. Okay. It depends on the experiment and the efforts. So in an observation season, you are observing in the day and at night. Something about, again, that's not intuitive about CMB measurements is that you can measure during the day. Mm-hmm. You just have different systematics to account for, but it's not like an optical telescope. Yeah. And you have weather to contend with. You have different variables of which arrays you had fielded, meaning what instruments were actually observing, what data can you work with, and then you combine that all into a data set, analyze it, come up with your map making technique. That evolves over time as well. People publish papers on how maps are made. And then finally, once you have a nice benchmark of body of work, you can create a new map, new data release, and announce it. And usually that announcement will accompany a lot of science that has gone into the work. For example, for the recent data release from the Atacama Cosmology Telescope, there are all of these papers that are kind of a sibling set that come along with the data release. So you say, here public, here are the maps. You can work with them now. Here are our results that we've worked on for years at a time. So I'd say that's a kind of the cadence is a chunk of effort at a time.
Okay, that's very interesting. Yeah.
So, slightly zooming out, how does on a fundamental level, how does large scale exploration of the sky, how does that probe fundamental physics different from colliders smashing particles together? What's the difference?
Yeah, we're probing some different energy scales. Like I referred to earlier in the conversation, we were talking about inflationary energy scales being orders of magnitude higher than we can achieve here on Earth. So energy scales are different. Length scales are different. And one of the coolest things about physics is that you come up with these properties that should be invariant across time and space, right? Like an electron is an electron. It doesn't suddenly become a different electron if you put it over there. Right. And so we can probe large scales, whereas earthly laboratory experiments probe smaller scales and check consistency of physical laws across kind of time and space. Right. And then, we can look back in time and see the way things have evolved. The universe's composition, how does that evolve over time? What is a dominant effect at any given time? Learn about complementary probes for that. The standard model of cosmology and the standard model of particle physics should hold throughout the universe. So insights in one time in the universe's evolution should give us some insights into today's physics as well. But I'm not sure that's exactly what you're getting at.
Well, kind of. I was, again, trying to understand that, how both these experiments are probing fundamental physics at different levels. So how do they sort of, how do they talk to each other? In some sense?
Unifying these scales of physics is one of the biggest open questions that we have in the field. And so when you're operating any experiment in any realm of physics, you know what your boundaries are theoretically, and you know the unknowns. So, for example, quantum gravity. We do not know how to unify quantum physics with general relativity. Right. Those exist at these different scales. And probing various elements of physics in different regimes, be it at a particle accelerator or in cosmology, gives us tools to test theories, but there is no one thing you can study to make your grand unified theory. You have to interpret the data with the theories that then join them. So theorists need to come to us with theories that we can then give our information and say, yes, that would work, or no, that doesn't hold. One exciting area right now is the tensions that we're observing in cosmology, where this is the types of cracks and clues that we need for theorists to stake their claim on explaining what is going on. So to give a nod to this, for example, the Hubble tension.
Yes.
When you're looking at late time observables in cosmology, you get a different answer for how fast objects are moving apart from one another in the universe than you do when you look at the cosmic microwave background. Tensions like this are how new physics is discovered. So we can explore that in various length scales, energy scales, etc. But we all need to talk to each other as a physical field through theories that then tie the results to one another. So if there's a laboratory experiment here on Earth that tells you what a particle has to behave like, and you plug that into the equations that feed into your early universe model, you shouldn't see a discrepancy if you're correct. And if you do see a discrepancy, it's exciting because you could come up with some other explanation. But this is all to say we need more data across length scales, time scales, energy scales to try to work towards a grand unified theory.
So that's precisely what I kind of had in mind, that, different experiments can lead to these different tensions or paradoxes, but then that basically means that, there has to come up, people have to come up with a way to unify these two ideas and understand why they're giving different results, and then try to come up with a method to unify them. That's great. Again, sticking to this probing fundamental physics, what signal in your opinion would, let's say, would be a smoking gun for breakdown of general relativity or modified gravity or neutrino masses and so on? What specific signals would do that?
So if we're looking at large-scale structure probes, like you just mentioned, we're looking at secondary anisotropies, typically like the SZ effects or weak lensing, which we didn't get into in this conversation so far, but photons have to traverse gravitational potential wells on their way here. That information gives you a really interesting map into dark matter across the sky. So we've made some of those with ACT, for example. And if we were to find that the dynamics of the late time universe differ from what general relativity would tell us, which we haven't, we would then think, well, we need some new theory because general relativity is broken. Right now, you can never count out, a model until you have the data to prove that. So general relativity so far is holding, but also there are modified gravity models that you can test against or for, I guess, depending on what you're rooting for. But you take the data, you look at the data, compare it to the theory. So far, we are seeing consistency with general relativity. We don't yet know what dark energy is. So if we were to think about some dynamics in the way gravity behaves over time, this could be interesting. For example, like the dark energy equation of state is now questioned to, is it evolving in time? Is it not evolving in time? Right. That's another thing we can look at as we're looking at large-scale structure probes. So watching how these largest gravitationally bound objects and the large-scale structure, the web of material in our universe evolves in time, that'll tell you something about gravity at large.
Right. So looking forward and looking ahead, cosmology and astrophysics still have some of the most biggest open questions. What do you think will be, in your opinion, in the next decade we will be able to answer?
Well, we have a lot of hopes. What the universe will give us is still to be determined. So, like I said, we're going to be probing new regimes of the tensor to scale ratio. It could be that we get a measurement of that. Certainly, we're going to be making better measurements of weak lensing and the Simons-Observatory effects. This is exciting because secondary anisotropy signals like these that are small signals were previously in the realm of theory alone. We didn't even have sensitive measurements of these until some years ago. For example, the kinetic Simons-Observatory effect is the signal encoded by gravitationally bound structures like clusters moving around and their velocities, Doppler shifting the CMB photons. That was not detected at high significance until recent years. And that will become a new tool that we can suddenly use as a significant probe for cosmology parameters. So we are looking at, for sure, seeing a lot of new secondary anisotropy signals that we haven't been able to leverage before. We're also going to be seeing incredible foreground handling. We'll move into a systematic dominated regime where we have to be very careful about all of the inputs in a way that we weren't previously just because we lacked the sensitivity for that. And with all of this, we're going to be making the best measurements ever of lambda CDM parameters. We're already doing that. We'll continue to do that. And by making those envelopes smaller and smaller, we're going to be able to see these tensions come into full effect.
Right.
So what that will tell us, we're not sure yet, but that's also exciting. When you have a very sensitive probe and you say, it's definitely this number, like there is really no envelope here to have any uncertainty anymore, and this experiment says, no, absolutely, I see something else, that's where exciting breakthroughs are going to live. So we see that in the Hubble constant. We also see it in the way matter clumps overall. So we'll see some information there. What that is, no one can say.
Right. So now, pertaining a little to devil's advocacy, why do we need all of these experiments working in parallels? And because they're not just running in parallels, these are huge experiments which take a huge amount of funding to work. The scientific advancement that it brings, is it worth the investment that we do?
Yeah, so that is basically our job as faculty members and people at these labs, is to convince people that they should give us money to build these things.
Absolutely.
And part of the reason CMB Stage 4 is not going to proceed is because we didn't argue that to their liking, that this was going to give the return on the dollar that we wanted it to give, in the opinions of the funding agencies. So I can say that any experiment that has come to light typically lives in a niche that is otherwise unfilled. You design these experiments to target certain frequencies, to have certain properties, to make certain maps that otherwise would not exist. For example, CCAT is going to have the widest field sub-millimeter coverage that has ever been built. And so you say, why should you build these? It's very expensive. It's if you want that information, you have to build the thing. So there are very few redundancies. There are very many complementarities.
Right.
So we're definitely leveraging the data sets from all different frequencies, including optical surveys. A lot of what I just mentioned about secondary anisotropies come about by cross-correlating between CMB experiments and optical or other probes. So we definitely leverage the complementarity, but really there aren't many examples of a redundant experiment because they will get funded because we can't convince people that they should be.
Yeah. Great.
So what is like an anecdotal pitch if you want to pitch something like why funding such a telescope should matter?
If we want answers to some of humankind's biggest unknowns, we need to build new telescopes. So it's a fairly binary choice to make where we have this exciting dark energy, dark matter, gravity, particle physics, evolution of our universe. If we want to know anything further, we need more sensitive measurements. If we need more sensitive measurements, we need new cameras and telescopes. So it comes down to, should we investigate the nature of our physical world?
So this is a nice segue to the tail end of the podcast, and what encompasses this is effective science communication. And you're an active science communicator. You're also writing books for kids and introducing them to the mysteries of the universe at such a young age, which is fantastic. How important do you think science communication is, and do you think it should be part of almost like part of a curriculum for every academician, especially for STEM, given the current times? Or do you think should it still stay a personal choice? Some can do and some cannot do.
That's a great question, and one that we talked about at this recent science communication workshop on quantum physics that I was just at last month, where we were lauding science communication for society at large, for introducing new people into STEM. If we want to harness the full power of human minds, those people need to feel like they have access and can contribute. And for me, that started from childhood, and I really want to break down those barriers for the next generation by telling them that you have a place in science, you can contribute. I think that's the only way we're going to have the door open to the next generation of breakthroughs from these future leaders. And in terms of mandating academics to be science communicators, I don't believe everybody should be a science communicator,
Okay.
but I do believe that everybody does communicate science. So I do think it should live in the realm of personal choice. However, if people are a little curious but not yet experienced with it, I think there could be so many more resources that would serve those individuals. For example, graduate students who are just starting to be like, oh, should I do an outreach event or something like that. Taking any kind of structured science communication course or workshop was critical for me in graduate school. And I think we could start that at earlier ages. We could do that in college, for example, just incorporating course elements like talks, presentations, written communication skills that can be worked into curriculum across any age. Right. And it's key for professional development. So one thing I like to say is you're not just communicating science with the public, you're communicating science to each other, you're communicating science to your advisor, to your classmate, to your friend.
Exactly right.
If you're talking to a person or writing something, you are doing science communication. So all academics are communicating science. If they write a paper, everyone can do it better. I don't think everybody needs to be on a podcast. As much as I would love to hear from everybody, I think you have the right to not do that.
That's fair.
So what motivated you to write for kids?
I really want to reach people when they are the most reachable. And I feel like society sets up all these expectations on young people so early, so frustratingly early, that we have, gender-coded toys when you're 2. It starts immediately. The expectations that are put on young people according to various factors, including economic factors, right? It's, scientists and academics, like, those are not people like us. People like us do this. So that's what you're going to do. And when you're a kid, I mean, that's all you're hearing from your parents, your classmates. You don't want to be a weird nerd if you're into something that's kind of different, right? So if you try to level the playing field a little bit at an earlier age, I think that gives you the most benefit. I was involved in a science workshop for middle school girls. And I asked some of them on the first day, I'm like, are you interested in STEM? And I got the answer, oh no, I'm too stupid for that. And it broke my heart because they're 7th graders. You're in the middle of your education. You're not too stupid for anything. You can learn about anything you're interested in. And that just tells me that that's a point where already you've gotten so many messages. Like, I'm not a math person. I'm not a this. And for me, it's not necessarily about getting everybody into STEM. Again, I don't think everybody should be on a podcast if they don't want to. I don't want to force people into doing anything they don't want to do. But I think true equality for me would be any person feeling able to do it. So it's like, if you can't see anybody who looks like you, know that it's even accessible to you, have your parents say, yeah, no, you could. Here are the downsides of that. Here are the downsides of the other choice. Like, if there's not an equal playing field, then we're not going to get everybody who could participate. So it's not even about more of X or Y in STEM. It's just having people feel they can participate in anything they want to do. And so that's part of the messaging I want to give to very young people, is just like, look at all this amazing stuff in the planet. Like neutrinos, what the heck are those? That's wild. What else is there to think about? And I'm hoping that by creating an accessible level resource for students who might otherwise feel intimidated by something as complicated as physics — I was intimidated when I was starting out — that it kind of opens the door for them to build some confidence into doing something like a pickup truck. That's a complicated thing too. But if you start to say, oh, well, I could learn about a particle, maybe I can learn about this truck, just building confidence and accessibility, and then having people take that where they will.
How did you find time to write books in your busy schedule? How do you do that?
That's a great question. So first of all, I will say the time lag on these books is quite large. I wrote the first one in 2016, 2015. So it takes many years to work through the publication process. So a lot of them were written a while ago. But for me, writing, and especially, so these kids' books are poems, they rhyme. I just have this kind of tumble out of my head on a Saturday morning. I'll just be like, "Wah," and then there's a poem. I just kind of vomit up the poems. So I don't necessarily sit down. That was actually a great challenge of editing them, is I had to, on a schedule, have my editor say, please write this many things and write it by this time. And I had to sit down and be like, oh, creativity. And I gained so much respect for creators who are needing to do these things on a schedule.
Constantly doing it. Right?
Yes. And people, now I have friends who are writers, and oh my gosh, the pressure of write really well right now, it's huge. Yeah. So I respect the heck out of people who are professional creators, because it's hard. I tried to work it in where I can. And that goes for all of outreach. So participating in conversations like the one we're having right now, or for example, we just had this great outreach event to the community looking at the sun with solar filters on a telescope. I try to make that a part of my weekly, monthly job, because for me, it's one of the most inspiring parts of my job. It re-energizes me. It contextualizes everything. It's kind of silly how we can grow so numb to the things we do every day, where it strikes me every time there's a telecon and it's like, well, did we avoid, the moon correctly? Is it the sun avoids? Like, this is so cool. Like, we're working with telescopes and avoiding the moon. Like, that's just so fun. But it's so easy to suddenly just feel like that is old hat.
Right.
So when you talk to people, it's especially with the CMB, it's like, oh yeah, I study the most ancient light in the universe, and that just becomes normal. And so when you tell somebody, it's like, I'm studying the most ancient light in the universe, they're like, that's so cool. And you're like, that's right, it is so cool. So it really energizes me and gets me through whatever hard parts of the job I'm working with at the time. And so I try to build communication at large into my schedule wherever I can.
Wow. Were the Physics for Babies books an inspiration?
So I definitely referenced those when writing my books, but they're very different. Mm-hmm. So I put a lot of long form back matter into mine, like little paragraphs on everything. And also the For Babies books don't highlight modern experiments to the same degree. I really wanted something that showed what you could get your hands on if you go into the fields. Mm-hmm. And that's something that was really missing. Like I read lots of books as a kid. Yeah. None of them were like, oh, this, neutrino experiment exists. Yeah. Right. Mm-hmm. That was very much for adults, Mm-hmm. It's like, you'll get to that later. It's like, well, I want them to get to it right now. But the babies books are really cute as well. I don't mean to put them down. I think it's a different niche, It's big blocky things for a younger.
Yeah, very visual.
Very visual, simple. It also helps familiarity with the words. And I think that's great. Yeah. So my books are technically for an older audience, like around 7 years old or so. And when you hit the kids young, which I love to see babies reading these books, even mine, to just say neutrino. Like anytime there's a video of a baby saying neutrino, they're so sweet. I think familiarity with the word, the baby's not going to know what a neutrino is. And that's okay. It doesn't need to know. But they need to feel like it's not a scary word, and that'll prime the neurons for later.
Yeah, I mean, if they're familiar with the jargon, that's that's great. And I think this also is reflected in physics education in general. And by that I mean an undergraduate is trained pre-1925 physics, and a graduate student is trained pre-1970s or 80s physics. And then at many schools and at many levels, sometimes they forget that it's also important to introduce what's going on right now, before they enter research groups and so on.
Right.
Sometimes people enter research group and they're like, wait, what?
Yep.
That wasn't taught in one of my core courses or something. Yeah.
Definitely. And this is why in my teaching statement, when I was applying here for this position, I was writing about incorporating modern research into teaching. And that's because I think it's really very important to contextualize why we're building these toolkits. I mean, you learn math and physics, you're building a toolkit. What are people using this for? And it's critical for students who are going to go into STEM to understand what their options are. It's also critical for students who are not going to go into STEM to understand what they're getting out of a physics and math education.
Right.
And so not only is highlighting modern research, I think, crucial, also talking about the problem-solving skills that you are developing in terms of how they apply to the real world. I think that's also very important.
Absolutely.
Yeah. So you're actually the first woman guest of season 2 of the Nomads podcast.
Oh my gosh, what an honor.
So how about you talk about your journey as a woman in STEM, and what would your advice be to young researchers, especially women in this field?
Yes. So I felt this very heavily, especially in my early college years, where I had a set of stereotypes in my head that society puts in our head. And I remember being a 16-year-old. When I started college, I was 17. And I just felt like I'm a 17-year-old girl. I don't know. What do you mean I'm going to be a physicist? It just was kind of incomprehensible. And I was doing it because I was just really interested. But I think it should not be on an individual's personality to overcome that. You know, I have a personality where if something is really hard and intimidating, it excites me. That shouldn't be a prerequisite, I think, of involvement in STEM, where if somebody thinks, I'm just a 17-year-old girl, what the heck am I supposed to do about this? Like, I'm just going to do something else that I feel like is less intimidating. I don't know if that should be a gate for physicists. Do you know what I mean? So that's one thing that I want to break down. Another thing is I had very few role models, especially ones who were like cool. There was this, you know, there are female scientist examples, but I, you know, this was a while ago now. I think we're doing a better job with, I think TikTok and Instagram have actually done a really good, social media has been positive for this. We now have people who are cool seeming scientists communicating with people, but at the time really not so much. So I was like into sci-fi because there were some cool women examples. So I think role models matter, representation matters. And when I was taking these classes, I would go in to take my exams in college and I would look at a bust of Nikola Tesla and his face would be at line with my face and I saw my face reflected against his face and I'm like, I just don't look like a physicist. I mean, first of all, I'm not a brass statue. Second of all, I have really long hair and like I just don't know about this all, you know. So it was kind of it was intimidating to be surrounded by all these images of old men and astronomical instrumentation that I didn't understand as I was going into tests. And so that was another thing that I had to be like, okay, like we'll just get through this day by day. And so I think having images around that support people's inclusion and you know, I'm so thrilled that the Rubin Observatory is named the Vera Rubin Observatory. Things like this just give a nod to the incredible women who have come before us and who faced so much more adversity. Like that's the horrifying thing. Anytime you talk about how marginalized groups are treated, like looking back just some tens of years ago, what people had to contend with, like that, just recognizing their contributions and labor is key because my
and
gosh.
Even like physicists, like we talk about Einstein or Tesla, like they're every time they're on the tip of our tongues, but we don't talk about Emmy Noether like that. So it and you can just, a kid knows who Einstein is, but they don't know who Emmy Noether is.
Yes.
So I think what you said, I totally agree that representation matters, and you're doing a great job representing all women in STEM.
Oh my gosh, thank you.
Thank you for doing this.
Thank you. I'll say one more thing because I think having people recognize that their skill sets are not just a happenstance, but a key tool of how they can participate in physics is really important. So I loved talking with people. I wanted to be social in my job. I think when you're talking about individual geniuses like this, you completely step away from that type of personality.
Exactly.
And so I thought like, okay, well, I'm a social person, but I guess I can put a lid on that and like not do that and be a physicist. But instead that actually is a core part of our large collaborations. We have to be talking with one another and working together collaboratively. So I think having more communication of what diverse interests and abilities and skill sets have a role in playing in modern research is really important. So there's a niche for lots of different individuals, and some people never want to talk to anybody else and they're going to contribute amazing things. Some people really want to work with their hands, they're going to contribute amazing things. Some people are coders, some people are communicators. We have to include all of these skill sets.
No, that's true. There's not a single mold where you can fill in, okay, that's a physicist, that's not it should be. Yes, totally agree.
Yeah, and we should definitely break that stereotype, which is genius sitting in the corner, like that's I don't think that science happens that way now at all. I mean, you said these collaborations are its own social thing, and you have to communicate, collaborate with people even outside your area of expertise, and you have to understand what's going on, and still come up with a tangible result and make progress.
Yeah, exactly.
And I think, the times are changing. I believe before, if you dressed a certain way, you weren't taken as seriously if you weren't looking like a physicist. So I feel that's very important, that you can look however you want and still know what you're doing.
Yes. In my freshman year of college, I pretty much exclusively wore sweatshirts because I just wanted to like
Yeah.
conform, you know. I put my hair back, I put the sweatshirt on, and that's actually part of my joy of being faculty now. I get to wear pink all the time.
Yeah.
I get to wear dresses, and I didn't want to wear a dress for a really long time because I had that image in my mind of a physicist, and they weren't wearing a pink dress, and I'm like, here I am.
Yes.
And it's fun. Yeah,
Totally.
It's great.
Well, Eve, thank you for doing this.
Thank you
Thank
so
you
much for
for-
having me. This was lovely.
Absolutely. Thank you. It was a pleasure having you on the
Oh,
podcast.
thank you so much.